Hello, my name is Clara Boanova and I am sales manager at m&opartners. I hope that you and your family are safe and healthy. Welcome to our Technical Thursday. Every Thursday, 10 a.m. local time, we receive a different partner to present their solution for maritime and oil and gas industries. Today, we have Lufkin with the safe and reliable gearbox operation. I would like to introduce you to our presenters. Mr. Francis Moss, UK Sales and Growth Leader for the Lufkin Power Transmission business in Baker Hughes. Mr. Francis has more than 30 years experience in the manufacture, operation, and maintenance of industrial and marine gearboxes. He's currently based at Allen Gears in the UK and works worldwide supporting customers and the Lufkin Power Transmission teams in France and Texas. Mr. Darren Swartz, Senior Sales Manager for the Lufkin Power Transmission business in Baker Hughes. He has more than 35 years experience in the oil and gas business and has held leadership roles in the Lufkin business, including European Sales and Market Leader and Senior Product Manager for the Lufkin and Allen Gear business. He is currently based in Houston, following previous assignments in Europe, Latin America, and Northeast US. After the presentation, we will have some minutes for question and answers. I hope you all enjoy it. Thank you.
Okay, so apologies everybody again, slight delay there. Good morning, good afternoon everybody. I'm Francis Moss, as Clara said, the UK services leader for Lufkin Power Transmissions Group, and we just want to give you a brief presentation on the safe and reliable gearbox operation. Darren's on the call and Darren will be in and out as needed. So first of all, just some gear basics, so everybody is familiar what we're looking at. We've got three basic designs of gears that we produce, overhaul and maintain in Lufkin. The first is the basic parallel shaft axis. This is a single helical gear, large ratio, as you can see, running in white metal hydrodynamic bearings. The middle, the angular gears, also referred to as bevel gears, right angled, often seen in things like water pump drives, cooling tower drives. And then the final one on the right hand side is the epicyclic gear, different technology, a little bit more compact, inline, and we manufacture and overhaul various configurations of both parallel shaft, epicyclic, and also combinations of the different units as well, depending on the application. So just a few words on the actual operation of the gears. The tooth meshing between the elements is a sliding and a rolling contact. Just to let you know, it's not a simple sort of contact sort of off and on. The teeth slide, and we'll show that in a little bit more detail. Obviously, to prevent the metal to metal contact, you need good lubrication, the right specification, and the right temperatures and the right flows, and we'll also have a few slides on that later. The actual gears themselves obviously have to be designed and manufactured to a very, very high tolerance to allow for the specific application. So the gears that Lufkin and Allen Gears manufacture are not off-the-shelf units. The majority of the units are designed and manufactured specific to a certain application. That may be a 1 unit or 2 units, or it could be many units in the identical, but they're always designed for a specific purpose. The materials obviously need to be strong. They need to resist stresses and also wear, and make sure that the gear lasts a long operational life. So this just demonstrates that action of the two rotating elements. As you can see, the gear at the top there, number 1, is actually driving gear number 2. As you can see, as the gears come into mesh, they first of all they slide and then they roll what we call a pitch line. So normally sort of the center element of the teeth, and then they slide out of mesh. So a few slides on lubrication in wear. So to keep the gear operating in its optimum and prolong its life, the oil has to do 2 jobs. It has to dissipate heat, so it has to cool the gears, and it has to lubricate the bearings and also the tooth mesh. So the basic functions is to reduce friction, and by that it reduces the wear. It cools, it removes heat. Definitely on the high-speed units, the majority of the oil's work is to remove the heat. It minimises corrosion and it seals against contaminants. So a lot of the units we produce have a very close fitting oil seal on all the shafts. So it stops the oil exiting the gearbox, but also stops contaminants from whatever operation it's involved in from entering inside the gear. And we'll see some examples later on of where gears have been contaminated and have seen detrimental effects on the actual rotors. So the gears and the bearings depend on this oil film thickness. We call it elastohydrodynamic lubrication. So this is where the oil is squeezed in between the rolling elements to a very, very high pressure. So once that high pressure is there, it will keep the metal surfaces apart. You don't want any metal surfaces touching together. We talk about an oil film thickness, and that's what we're talking about. It's that very, very thin microscopic layer of oil that sits within the gear teeth and also the bearings. And to be able to give an effective lubrication and cooling of the unit, the oils have to be in a good condition to the right specification and not contaminated. So things like oil sampling is very important, especially for high-speed gears, where you may have a very quick deterioration in the oil. So a couple of brief examples of different lubrication systems. The splash or gravity fed system on the left, as you can see there, literally uses the rotation of the gear elements to pick up oil out of the sump and splash it around the internal of the gear case. So as you can see there, the oil will then drip down into oilways, which are fed then into the bearings. As you can see, the bearings on that unit tend to be roller bearings or taper roller bearings. So this is where they're quite low speed and low duty, so slower gears. We can get away with a drip or splash gravity fed sort of system. The one on the right, we're now going to a pressurized system. So you can see you have external pipe work, you have things like coolers, pumps, filters involved in that, and that is when the oil here is fed into the gearbox under pressure. So this is now we're going to the high-speed units and the units that run on these elastohydrodynamic bearings. They're also what we term white metal. So the bearing does not have any moving parts. The shafts rotate within a shroud bearing that's has a white metal layer on the inside, and high pressure oil is fed into the bearing, which helps the shaft to float within the bearing, so there's no metal to metal contact. So again, gear reliability and life depends on the oil's performance. It will help reduce the pitting or give the gear resistance to pitting. Where you have metal to metal contact, the oil will give it longevity. We talked about the oil film stability, so the oil has to be of adequate viscosity and a condition to maintain that oil film thickness. Bearing performance, as we just said, the oil at the right pressure, the right temperature will enable the gear to perform at its best. The gear is designed to operate at certain oil conditions under certain pressures, so that needs to be maintained. Also, it avoids contaminants. So as we said before, it will help preserve the gear. It keeps the gear and the bearings in the best possible gear condition. So to be able to keep that gear performance, the lubrication of the oil needs to be of the correct selection. So normally in the manuals, you will have a gear specification. So that specification has to be met. Don't automatically think that one oil can be used in various different machines, because depending on the machine's design and the loading, it may have a different oil specification than perhaps your pump or your generator or your compressor. So the oil's chemical and mechanical compounds need to be checked quite regularly. A lot of customers will have a monthly oil sampling routine where they check for contamination, they check for metal particles, and make sure the oil isn't breaking down in any way. The oil checking will also give a very good early warning of any gear problems. We talked about gear wear and pitting. You can quite often pick up metal particles in the oil at one of the sampling times before or long before you have any indication of a gear that's got a problem. And we talked about cleanliness in temperature as well. Very important to make sure the oil remains in the best possible air condition. So this slide just shows you the stresses on a gear mesh. So you can see the two teeth. This one, if you look at the bottom set of teeth rotating clockwise, it's driving the top set of gears anti-clockwise. So you can see where the tooth contact, you have a very, very high compressive loading. So the blue areas on the two teeth, you can see we have two teeth in contact. So they're sharing the load. So it's very, very high surface stresses. You can also see, I think, in the root, if you look at the root of the teeth, you can also see a pale blue area there. So this is the bending stress. So as the tooth is taking the force or the torque from the driver to the driven gear, you can see that tooth is actually under compression in its root. So what it's trying to do is trying to bend, the top tooth is trying to bend to the right. So that's where we have to design the gear with the materials and the case hardening processes to be able to withstand these very high compressive and tensile stresses for the design life of the gear. So this is some brief explanation of the different types of gear problems you can have. So when we talk about wear, we talk about abrasion, corrosion, fretting, electrical discharge, and I'll show you some examples of those in a moment. But when you talk about abrasion and corrosion, you can normally spot that on the teeth. Also scuffing, another form of wear, so that the actual mating parts of the tooth where they slide and roll into mesh, you can get what we call scuffing, whereas the metal particles will start to come away. Very similar to plastic deformation. So this is where the gear is being stressed beyond its elastic limit and it's starting to deform. So very common on low speed gears which have a through hardened material. So it doesn't have a case hardened layer like a high speed gear. So you can get a lot of plastic deformation. So the gear will start to deform and you can start to see the metal being pushed away as it's trying to resist the torque of loading. Contact fatigue, as we saw before, the stress levels on the profile of the teeth can be very, very high stressed. So you can start to see pitting, what we call macro pitting, and then it turns into micro pitting, so the next sort of level up. And then eventually, if nothing's done and it continues, it can cause sort of subsurface fatigue and cracking, and you can get the surface of the teeth cracking away, pitting quite badly, or even the whole section of tooth failing and breaking away. So the bending fatigue, very similar. We saw earlier on the stress slide. In the root of the teeth, you see a very high blue concentration of compressive stress. This is the bending. So this is the gear tooth trying to bend away from the load. And you have a life that the gear is designed to do. So the low cycle fatigue and high cycle fatigue is to do with the gear's design to resist this bending fatigue of the teeth. Then we come on to cracking. So this is what happens after micropitting, or can happen after micropitting. If it's ignored and there's no remedial action, you start to get cracking in the hardened case layer. Grinding cracks tend to be a manufacturing issue, not a operational issue. So we check very carefully at various stages of manufacture for grinding cracks. Obviously, if you get cracks in a newly manufactured gear, that will limit its operational life. And so we are very careful with crack detections at various levels, pre and post machining and pre and post finish grinding, especially on hardened gears. Rim and web cracks happen on the low speed units where we have like a welded rim. So to save weight a lot of the times, and also to save cost, you can have a hardened gear rim put onto a fabricated sort of central gear core. Also fracturing, as we said before, there is a point where the gear will fail and you can get fracturing of subsurface your materials, and you get fracturing of gear tooth ends where you get the loading will run off the end of the teeth. So we design the teeth with various corrections, just try to share the load evenly to stop that high buildup of stresses. So some examples of wear. So you can, I don't know if you can see on the tooth profile on the right hand side, you can start to see some lines and scuffing starting to appear. So this can be normal operation. So on some gears, normal wear is seen throughout the gear's life. If it's not severe and it's not deteriorating, then it's a part of the gear's operation. Obviously, if we can catch any abnormal wear quickly, we can perhaps do something about it. We can do various maintenance, polishing, regrinding, which will help the longevity of the unit. There's various different levels, as I said. We can get onto some more severe in a moment, but mild wear, as it says, it can normally be considered is acceptable depending on obviously the level. So this is more severe wear. So this is where you're getting more of a scuffing wear. As you can see, the profile of the teeth is starting to exhibit signs of metal to metal contact. So you can see the lines along the pitch line, as we call it. If you look at the second and third tooth up from the bottom of the left-hand picture, as I mentioned before, you get a sliding action in the tip of the tooth and then a rolling action over the pitch line, and then it slides out of mesh. You can see there, you can definitely see a line on the pitch where it's rolling. So that would indicate perhaps a breakdown of the lubrication oil or perhaps an overloading of the gear. On the right hand side, you can see an example of severe abrasion. So this is where you have metal to metal contact, and you can see the gears are actually running together without any or very limited lubrication. So that gear is in serious distress, and if that continues to operate without your remedial action, then that will only progress and get worse until ultimately a major failure of one or more of those teeth here would occur. Examples of other gear problems. On the left hand side, this is corrosion. So this example is chemical corrosion. So this is one of our gears that we've had in the chemical works. It's got contaminated, perhaps one of the seals is leaked, and it's got chemical contamination. You can see on the tooth profiles are now very pitted, and it looks like they're under corrosion attack. On the right hand side is what we call electrical discharge. You can see that there's like what we call tiger stripes across the teeth. And this is where you have an electrical charge build up in the rotating elements. And basically what's happening is there is very minute electrical discharge sparks basically between the two gear mesh. So as the gear comes into contact, you've got that very, very fine oil film thickness. It's thin enough to allow the electrical energy to discharge across the two gears. And that's what you'll start to see, this striping effect. And if you look at it under a microscope, it's like a mounted, very, very small mounted pitting sort of effect. And that's what we call electrical discharge. You can also see that on bearings. It obviously discharges across the smallest gap, which tends to be either on your gear teeth or on your bearing surfaces. So insulation in maintenance. Very, very important to keep the gear clean. This is an example of a spare part that hasn't been stored here very well. It's been opened up and left to the elements, and you can see corrosion and pitting is starting to attack that gear. That gear would not be suitable yet for service, because you can imagine it would deteriorate very, very quickly. So it's very important to keep both the gear when it's operating and also any spare parts, any spare bearings, very well preserved and sealed as much as we can until it comes to operation. Lufkin and Allen gears, when we supply spares into the field, they are normally preserved. They are normally covered in like a wax oil or wax paper, and then vacuum sealed inside a foil vapor barrier. So that's to protect the parts for long-term storage until they're fit for use. So just a few comments on the importance of installation. Obviously the gear can only operate if it's held and aligned correctly within the equipment. So it has to be very, very tightly secured so it doesn't move, because you can imagine a lot of these units are taking many, many megawatts of power. So they need to be aligned and then held in that alignment throughout their operational life. The integrity of the mounting surfaces is critical to the gearbox. And it just gives some indication of how the gearbox has to be leveled, and various tests need to be performed on things like soft foot checks to make sure the gear isn't distorting, and it's kept in its optimal operating year condition. So the reason for that is to maintain your tooth contact marking. So you can see on the left hand side here, we have some examples of tooth contact. If you look at A, which is the top one, as you can see, we have a full contact across both helixes of the gear. This tends to be a double helical gear. So that's the ideal contact mark. So the load is shared across the whole width of the gear. It's not concentrated in any one place. So as you go down that list of contact marks, you can start to see we're starting to get heavy marks in the middle or heavy marks towards one end of the teeth. Now, obviously, if that happens, that section of the teeth that is in contact could possibly be overloaded, and that reduces the life of the gear. Just above that, you can see the schematic there. Obviously, when we align the gear, we have to take into consideration things like thermal and mechanical movement. So thermal growth. So if you look at the manual of the gearboxes, it will normally have a shaft alignment schematic, which will take that into consideration. So when the unit is operating at full power, full temperature, it will be in the optimum position. We can check that tooth contact with what we call an engineering blue. So you can paint blue on the teeth, you can run the unit at full power, and then through the inspection covers you can quickly check that and make sure what the contact is, and you can correct it if needed. So it's just some examples of some blue contact marks, as you can see there on the left hand side. So this is how we take them, and you can see we have some good full contact marks on these teeth. On the right hand side, a schematic of the manufacturing process. So as you can see, we allow for things like torsional correction on the loaded side of that pinion there. So that loaded side on the right hand side has correction on it to allow for twisting of the gear under the correct load. So maintenance, we have various recommended maintenance strategies depending on the gear, depending on the application, and obviously the power and the arrangement of the gears. This is just a general one, just to show you what we normally recommend. We recommend a full inspection of the gear unit around every 5 years or 40,000 operating hours. And then in between those, regular vibration surveys and perhaps in situ boroscope inspections, where you use a boroscope through the inspection covers just to make sure the gears, the contact marks, are in their best possible gear condition. So just a few words on vibration noise surveys. So we can take these, the Lufkin and Allen Gears engineers can take these on site, or customers can take them themselves and send us the resulting reading, so we can help analyze, and we can also advise on any trending or any limits, sort of alarm and trip limits for a specific gearbox or package. Also, we offer full in situ inspections, so we can strip the gear down to its component parts, we can clean it, measure it, inspect it, and then put it back in for further service and recommend any replacement parts or any remedial action you're required. Full inspections. So again, this is where we can take a unit, we strip it down, we can replace parts. We can also offer drop-in replacements for end-of-life units. But this is where we can check everything connected with the gearbox. So that's the end of the presentation. Sorry, I had to rush the last few slides. We'll make a few times, but I hope you found that interesting and informative.
Okay, the first question is from a gentleman from Petrobras. Please provide recommendation on acceleration direct vibration limit for a model NFQ 3119E gearbox. There are always on high-speed gearboxes recommendations from the manufacturer on the drawings that give you recommended alarm and shutdown points for vibration, proximity probes, acceleration, and depending on the application and the installation of the gearbox, those recommendations are generally just a starting point to establish a baseline for the gearbox. What we would typically recommend is that we consult the original design of the gearbox, and then what the measurements were during the factory acceptance test, and then what the measurements or amplitudes were during the startup and commissioning of the gearbox. So the values can adjust depending on the type of installation, and the it can even vary from one package to another on similar type gearboxes. But we can address that if you'll be in touch with Clara or the team from M&O. We can get some serial number information and have a more specific discussion about your particular gearbox.
Thanks, Darren. There's one there about what is the expected operational life of a gearbox. I'll try to answer that. It depends on the application and the customer's requirements, but just to give you some examples, On the Allen gears high-speed epicyclic units, we tend to design them for an operating life of 100,000 hours. So if you take that as 8,000 hours a year, 24/7 continuous operation, you're looking at around 12 years of non-stop operation. Now that's the design life. The expected operational life is many, many times more than that. We talked about earlier about the importance of the cleanliness of the oil and regular inspections. We have high-speed gearboxes that have done in excess of 250,000 operating hours. So you're looking at 20 to 25 years and they're still operating now. So it does depend on what the gear is designed to do, but as long as it's maintained and serviced, it will operate for many, many thousands of hours.
The next question, do you have any minimum recommendations for monitoring the condition of gearboxes? We always have some thoughts around how to protect and monitor the health of the gearbox, and unfortunately, it's linked with the type of equipment, whether it has hydrodynamic bearings, white metal babbited bearings, or anti-friction bearings, the type of application, and the driver and driven equipment. The plant owners and operators can influence the level of instrumentation for gearboxes, but generally speaking, on an industrial gearbox, what we would consider a low speed pump reciprocating machine type application, it could be as simple as casing acceleration or velocity, and maybe as simple as sump temperature of the gearbox. If it has a pressurized lube system, we would want to monitor oil pressure and temperature on the supply side. And then if it's a full API type piece of equipment on a compression or offshore platform, those gearboxes would have a much more extensive vibration temperature monitoring system, including embedded RTDs or thermocouples, and then a full complement of proximity probes and accelerometers.
Okay, and there's another one here. It says, what maintenance recommendations would you have for high-speed gearboxes, and what would be different for low-speed gearboxes? That's anonymous, but if you want to get in contact again, we have a set of generic recommended maintenance procedures for both high-speed, parallel, epicyclic, and also low-speed parallel and epicyclic gearboxes that we can give you. We can provide those. It goes in a lot more detail of what we recommend at different levels, but the main difference is on the low-speed units, you tend to have anti-friction roller bearings. Now, in some cases, for very low-speed gears, they will be designed to last the life of the low-speed gear. In other cases, those roller bearings will have what we call an L10 life. So there may be regular maintenance on a low-speed unit, perhaps every 5 or 7 years, to replace all those anti-friction roller bearings. On the high-speed gearboxes, we tend to have the white metal hydrodynamic bearings, which are designed to last the life of the gear as long as they're not damaged or we have any sort of corrosion issues. But if you want to reach out to us, we can provide you with those detailed recommendation maintenance here for those units.
Okay.
Okay, but thank you everybody for your time today, and I hope you found that informative and interesting.
Thank you. Thank you, Francis and Darren. And see you next Thursday with our Technical Thursday.